Okay, let me share my screen. Nikesh, can you confirm whether you are able to see my screen? Okay, thank you. Okay, let me go to this. Okay, fine. Okay, as I mentioned in the NPTEL website, today we will talk about a written period, but it was supposed to be discussed on 27/9, but due to the health conditions, I could not able to take that session. So now we will discuss the same. So in this session, we will talk about the written periods, and we will solve one question related to that particular concept, and later we will solve two previous year gate questions, and these questions are related to the concept we have discussed in previous sessions. Like one is on a hydraulic jump, another is on a specific yield. So I hope this session will help. Let's proceed further. So okay. So Okay, so can you like observe this particular plot here? So this is a stream flow plot. X-axis is the time, y-axis is the magnitude. Let's say, suppose let's say we have this is like maybe this is observed at some gauge location. Okay, this may be observed at some gauge location. Let's say at the downstream of that particular gauge. Let's say imagine this is a river reach. Water is flowing like this. Now we want to construct a bridge here for a bridge. Okay, now we are wanted to construct a bridge, and this bridge should last for some years, like let's say t years. So like r n years, maybe r n years. So this bridge should serve the purpose for n years. So to perform this kind of exercises, like I mean to say that, like to design this bridge, we need to figure out the design stream flow, corresponding to this n years. Okay, so this particular stream flow we often consider as a random variable. So now I'll talk about what is a random variable, and how we can calculate the time period, return period and all. So random variable is said to be random if its value depends upon the outcome of a chance event. Let's say for example, you have a coin. Let's say you have a, let's say maybe coin or dice. Let's say dice will have a six faces. Okay, dice will have six faces. Let's say you roll the die, and your interest, like let's say x is one variable, which indicates the value observed during thrown, dice thrown. Let's say during dice thrown. Okay, let's say suppose when you thrown the dice once, you may get one. Suppose next time you may get two. Like that you can get a different value for each experiment. Okay, for each event. So that, so this kind of particular outcome we often denotes with a variable, but that particular variable is called as a random variable. Okay, that, see, typically we can use a x or y, any symbol can be used to denote the random variable. So random variable is will have a, it will have a values, and these values depends upon the outcome of a chance event. Okay, for example, like tossing a coin. So when like when you toss a coin, whether observing the head or tail, that is one variable. Like when you throw the dice, like observing the number, that can be considered as one variable. Let's say when you thrown a three, when you toss a three coins, number of heads, all these kind of outcomes can be denoted with a random variable. Suppose this is the general example. Let's discuss about our hydrology here. Let's say suppose here what are the event, suppose let's say our purpose is to design a bridge or design a culvert which should serve the purpose. It means that the bridge or a culvert should not be overflowed or overflooded. Okay, so what are the examples of events? Culvert capacity being exceeded or stage of flood flow exceeding the deck of edge. Let's say if these two are observed, then we say that a event is happened. So our interest is to design a structure such that we can predict the probability of occurring this particular event. Okay, suppose let's say suppose we design a culvert which serves for 50 years. Suppose we say that in a 50 years it the risk of flooding may be some value. So that kind of analysis we will perform here. Okay, these are the examples of event. One is like culvert capacity being exceeded, stage of flood flow exceeding the deck height of the bridge. Okay, so these are the examples. Now let's see what is the return interval. So return interval is nothing but time interval between any two occurrences of an event. So what is our events here? One is that culvert capacity being exceeded, that means that q, suppose discharge, let's say maximum, let's say discharge maximum greater than the q design. So this is the thing. Let's say observe this particular plot. Maybe like this particular black color stars on the top of a bar indicates the maximum value. Let's say imagine this is a culvert capacity, that is nothing but 50 meter cube per second, per example. Let's say now just observe the data and calculate the time between interval between the events has a stream flow greater than the design capacity. Let's say here this particular value exceeded the design value and this particular value exceeded the design value. Let's say the time between these two may be tau. The particular tau is nothing but a recurrence interval. So recurrence interval is nothing but a time interval between any two occurrences of an event. When we said occurrences means that observing the stream flow greater than our design or a danger level. Okay, so now the return period. So what is the return period? Suppose similarly, suppose here is maybe this is tau 1 and from this point to this point maybe tau 2, like that. Like if you see the the time interval between the exceedances is varying along the time. Maybe here is a tau n, here it is very large tau. Okay, tau max maybe. So if you observe, the recurrence interval between the two events are varying over the time. But suppose if it varies in this way, we cannot able to design. So what we do is that we will take the expected value of this particular recurrence interval, that is nothing but the return period. So t equal to expected value of tau, which is nothing but mean of recurrence intervals, mean of recurrence intervals. Okay, so rather than looking at individual recurrence intervals, what we do is that we will take the mean recurrence interval and we will say that on an average at least once the stream flow value will exceed the design value. Okay, like say for example, when somebody say return period is 50 years, what does it mean? It means that on an average at least once the q either stream flow value is more than the design value. So this is a very important definition you should remember for IAS exams. Like for GATE also you may expect it to ask, but in interviews, all the IIT MTech interviews and PhD interviews, this is a definitely important question. So the return period shows the average value for at least once that value, at least the value will exceed the threshold. Okay, so you must remember these 2 points. One is the average, another is at least. It means that at least once it will occur. It does not mean that like only one, like it can be occur 2 times, 4 times, 5 times. This is a common confusion we have. And one more confusion what they say that, let's say suppose in 1947 this event happened, let's say q event happened. So when we say this is a 50-year event, then people tend to imagine that 1947 plus 50 maybe 1997. After 1990, like after 50 years only this was another event. This is wrong. This is also a wrong perception. See, if you observe all these weather bulletins and all, they say that we observe 100-year precipitation event or 200-year precipitation event, especially if you look at the 2018 Kerala floods and all. Okay, so when we say some t-year return period does not mean that after 100 years it will occur. It is not that case. It is like expected value of occurrences of an event. It can occur in the next year, it can occur in the, like it depends upon the event, outcome of a chance event. Okay, so this is a return period value. So what is the probability of occurrence of an event? So how we can calculate the probability of occurrence of this particular event? It means that suppose probability of stream flow exceeding the threshold. Let's say we assume that xt is our design value and x is a variable, random variable. X is a random variable. Okay, so here probability will denote with the small p. This is a function, capital P function we denote with the capital P. So probability p equal to probability of capital X greater than or equal to xt. It means that stream flow is greater than or equal to the design capacity. What is the probability that can be related with the return period, which is nothing but 1 by t. Okay, this in this way we can calculate. Another way is that by observing the data we can empirically also we can calculate. That is also possible. So this is a probability of occurrence of an event. Similarly we can calculate the non-occurrence of event. As we know, uh, total probability always will be equal to 1. So f equal to probability of x less than or equal to 1 minus 1 by t. This is important equation. Okay, so let's look more details about it. How we can calculate the probability of occurrence of an event. Okay, suppose we have the stream flow data. Let's say this is a this is a time, this is a q value. Let's say we observe the daily stream flow value or a monthly or annually value. Let's say this is our threshold qt or xt, for example. Okay, let's say day 1 we have we got a this much stream flow, day 2 maybe this much, day 4 maybe this much, like that. If we observe, okay, now our interest is to, let's say our interest is to estimate the probability of occurrence of these particular events in a stream flow series. So now how we can do that? So that has a different procedure. So now we can see, like when we say for each observations in a peak flow time series, there are two possible outcomes. One is that either occurrence of event, it means that stream flow greater than particular value or less than that. Only two cases are possible. So how we can do? Suppose only two cases are possible. This is nothing but Bernoulli trials. So you must remember this from Max statistics subject. Let's say you have a coin. So what are the outcomes from a coin you can get? H or head tile. Okay. Suppose what is the probability of observing the H? We know 0.5. What is the probability of observing a tile? 0.5. Okay. Because when we say unbiased coin, this is unbiased coin. But this is the unbiased coin and we know the exact probability of observing head and tail. But here in this case we don't know what is the probability of observing p, so x greater than xt, and as well as probability of x less than or equal to xt. So what I mean to say is that here these probabilities are follows the Bernoulli process, and we can model this particular variable with the Bernoulli distribution. So I hope you remember this particular equation from the statistics. X equal to x equal to ncr p power r q power n minus this is a general PDF equation of Bernoulli distribution. So this is for, so when we say this how we can read that, suppose let's say you did the n trials. Out of n trials, how many times you got succeeded, so that will with the r, so a probability of succeeding. So this is a like so so in this case, how we can read this particular equation, what are the successes, what are the success in n trials or n independent Bernoulli trials. So in these kind of cases we use a Bernoulli principle. So this particular event is is exactly the case of Bernoulli trials, IID Bernoulli trials. So we can use this Bernoulli distribution. But in this case, we are interested in n r success. But in this case, our interest is to have only one success. It means that only one time the stream flow should exceed. So it can be narrowed down to this particular equation from NC tau to P tau q power n minus tau, like that. Like let's say from there to there we can narrow it down to this particular equation. So this we know, this is a recurrence and duration. But from the return period, what is the return period? Return period is nothing but expected duration, expected recurrence intervals. By performing this particular simplification, we can get p minus 1 from, so suppose this is equal, this is nothing but t equal to p inverse, so p 1 minus 1 by p, so from p equal to 1 by t. So this is a probability of occurrence of an event. Okay, this, in this way we can calculate the probability of occurrence event. See, this is a mathematical equation, but from the data, how you can calculate? From the data, what you can do is that, let's say you have a data of 100 years or 50 years and all, like so. So what you can do, you can calculate the recurrence interval series. Let's say tau 1, tau 2, and so on, tau 5, tau, like let's say tau n. From there you will calculate the expected tau value. From there you can get a capital T. So 1 by capital T will be give the probability of occurrence of an event. So once we know the probability of occurrence of an event, it is a piece of cake. So we can fit the model and we can proceed further. So this is all basic stuff now, but our interest is to calculate the risk. Risk, it means that at least once in its life. Okay, so a FUD control structure fails if peak flow exceeds xt. So when the flow is exceeds this particular xt, we say that our structure failed. So what is the risk associated with this one? This can be calculated with the help of this particular formula, which is nothing but 1 minus 1 minus of probability of x greater than xt in n years. Okay, in n years. So there is a long derivation for it, so you can ignore for a time being, but you can remember this formula. Okay, so r is nothing but risk, nothing but 1 minus p x greater than xt r whole power n. So otherwise I can simplify quickly, I can do that. Probability of x greater than or equal to x equal to n c1 p power 0, sorry, nc0 p power 0 q power n. Okay, this is a non-occurrence probability. So it gives the q power n. So from there, like if I want occurrence probability 1 minus q power n. So from this you can get this particular derivation where q equal to 1 minus p, which is nothing but probability of x greater than xt. So this it will confuse you a lot. So just remember this particular equation, r equal to 1 minus p x greater than xt whole power n. See, if you remember this formula, it is straightforward only. You will get a n value, you will know that this t value. So from there you can get a risk and probability. So here n is nothing but expected or design life structure. So by suppose if one want this we know that this is 1 by t, so 1 minus 1 by t, so we can reshuffle this terms, we can get t equal to 1 by 1 minus 1 by r 1 minus r whole power 1 by t. So just remember these two formula, it will be sufficient for your exam. So yeah, here I have given one table. So see, I'm running a little late, so that's why I'm moving fast. So for a design life, let's say 100 years, let's say t equal to 100 years, then what will be the sorry, suppose if let's say I have a design life of n equal to 100 years, then how much will my t value? So from that, like how much is my risk and how much is a t, I can calculate in this manner. Let's say if I have a t n here, and like by performing this here is nothing but 10, okay, and if I vary n is the here is n is 100, suppose you substitute some value and you can get a risk. In this way you can, like let's say risk can be vary from like a point, suppose let's say risk is 0.1, then corresponding to how much, risk is 0.5, corresponding to how much. So in this way you can calculate, and we can come up with either like a 100 year return period or 96-year return period, and corresponding risk also we can estimate. Okay, so now look at the question of 2022 set 2. So I'm moving fast. Let me see whether you guys are able to see. Uh, is it clear, or did I confuse you a lot?
Sir, it is absolutely clear.
Okay, fine. Thank you. Let me go back to the slideshow mode again. Okay, so this is question 28 from 2022 set 2. So in this is like not a straightforward question, like this is actually a result in you can observe in this, like you can get it from the textbook. So it is a straightforward result, like suppose a flood control structure having an expected life of n years, okay, is designed by considering a flood of return period of t years. Okay, let's say when t equal to n, let's say here I mean to say that, let's say if you observe this particular point here, if you see here, when t equal to 110, corresponding to design life of n equal 100 years, how much value you observe? 60. Let's say when n equal to 100 and t equal 96, how much we observe? 0 0.6. Okay, just keep these two values in mind. Let's say if t equal to n, and if t equal to n and n tends to infinity, okay, the structure's hydrologic risk of failure in percentage will be, okay. So can anybody guess how much will be the value? Maybe a approximate guess. I've given the hint from the previous table also. The value lies between 0.6 to 0.65 only. Okay, let's see how we can solve. Okay, so this we know, this I have shown you, risk equal to r equal to 1 minus q power n, q power n, q power n. See, this q power n is probability of non-occurrence of event in n years. Okay, our what is our risk? Our risk is what is the probability of at least once. Okay, so that's why we used 1 minus q power n. Okay, so q is nothing but 1 minus p q, so I can mention here p plus q equal to 1. Okay, this is one basic equation from a probability. So let's say this is a favorable outcome, favorable probability, this is a non-favorable probability. So the favorable probability plus non-favorable probability always equal to the 1. It's a basic probability law. Okay, so now this is so q equal to 1 minus p. So we'll substitute here 1 minus 1 minus p power n. So we know from earlier slides p equal to 1 by return period. Okay, 1 by return period. So substitute that 1 by t, 1 by t power n. Okay. So what they mentioned here in the question, given that t equal to n and n tends to infinity. Okay. What we do now, we'll just do some trick here. So what we that we replace t with n. Okay, so it will be limit n tends to infinity 1 minus 1 by n whole power n. So okay, now what we do is that we'll take this minus inside and put the plus, because why I have performed this, that we have this result, we have this result from BTech for BTech mathematics. So when limit x tends to infinity, 1 plus x whole power 1 by x will give the value of e. So we will shuffle the terms such a way that we can get this particular value, e exponential value. Okay, that is our aim here. So what we are doing, so now 1 plus 1 minus 1 minus will go inside, so 1 by n whole power n. So okay, now what we do is that let assume minus 1 by n equal to y. So n will be, so it can come down, so 1 minus y. Let's say when n equal to infinity, when n equal to infinity, what will be the 1 by infinity? It is 0. Okay, so that's why like at n equal to infinity, y equal to 0. So these are the like few basic mathematics from BTech first year. So I hope you are comfortable with that. Now we'll just use the same analogy here. So limit n tends to infinity 1 minus 1 by n whole power n. So it can be written as, maybe it will be confusing. In this it's fine. Limit, then we'll substitute this n y in place of n. So limit n y tends to infinity 0, 1 plus y whole power minus 1 by n. So because we know that n y equal to minus 1 by n. Suppose if I do n equal to, it will be minus 1 by y. So that's why it is here minus 1 by y. Now so this is like this. So what even we can do, this minus we can take it out. Oh, maybe I made a mistake here. This is 0, not infinity. So now limit y tends to 0, 1 plus y whole power 1 by y. We can write it in this format. So this particular result will lead to e power minus 1 as from the previous slide. So limit x tends to, in place of x you imagine y, x tends to 0, 1 plus x whole power 1 by x equal to e. Okay. So this will give the value of this whole, inside the bracket will give the value of e and e power minus 1. Okay, this is r. So r equal to 1 minus e power e power minus 1. So it's nothing but r equal to 1 minus 1 by e. When you enter this particular 1 minus 1 by e in the calculator, you will get a value of 0.6321. But in the question, it asks to write it in a percentage. So it will be 63.2%. Okay. Is it clear? Uh,
Yes, sir.
Yes, sir.
okay. So this is a result you can remember always. When t equal to n, the risk will be equal to 63.2%. This is a standard result you can remember, because many times you may tend to forward this limit result. So maybe you can by heart this particular equation. When t equal to n, the result, the risk will be 63.2%. So this particular table is depicting the same as like as t is becoming equal to n, the risk is increasing. Okay, so when exactly, suppose if I calculate 100 here, the value would be 0.63 only, 63. Okay, so this is about risk. There are other questions also that other questions are already the solutions of other questions are available in the NPTL, but for particular this question solution is not available. So that's why I thought to discuss in the class. So let's move to this question from GATE 2021 related to the hydraulic jump. So in the previous session we discussed hydraulic jump, and in the hydraulic jump we have seen that when the flow goes from the low pressure region to the high pressure region, this is a like bed. So this is a supercritical section. This is subcritical section. So when the flow takes place from the low pressure zone to the high pressure zone, the hydraulic jump takes place. And we even discussed the main three equations. One is that y2 divided by y1 equal to 1 by 2 square root of 1 plus 8f1 square minus 1. I hope you remember this particular equation. And another equation, what? Energy loss equation. Okay, y1 minus y2 whole cube into 4y1 y2. I hope I'm correct. Anyway, in the next slides I have shown. Yeah, correct. Yeah, so these are the basic characteristics of the jump we discussed in the previous session. So hydraulic jump will form in a channel if the forward number of the flow and the flow depth y and the downstream depth y2 can be calculated using this particular relation. I have written this y2 will be like so here. Let's see if I take section 1 2 here and the section 1 here. So here I'll have y1 v1 f1. Similarly I have y2 v2 f2. Okay, suppose if one know that y1 and f1 at the downstream, we can able to calculate the y2 and subsequently other terms also. So the question is essentially use this particular relation only. Like in the in every session, I am giving a three to two equations. If you remember those equations, that is sufficient to solve any type of question related to that particular topic. So maybe one suggestion I can give is that maybe like you keep one white paper next to you during every session. So when I say these equations are sufficient, maybe you can write those equations separately on that particular white sheet. This will be like a summary sheet where you will have all the important equations, so that you can have this equation on your fingertips when even in a sleep also you can have this particular equations in on a fingertips. Okay, now let's see the question. The question is as follows: a spillway discharge a flat flow at a rate of 9 meter cube second per unit width. Okay, per unit width. It means that they have given us small q. If the depth of the flow on the horizontal apron at the toe of the spillway is 46 centimeter, so you can write as 0.646 meters also. The tailwater depth need to form a hydraulic jump is approximately given by which of the following options. So the options are given A, B, C options are given. So essentially we need to calculate the y2 value. How much is the y2? Okay. So anybody can guess how much is the value? Just use this particular equation. This is equation is sufficient. Maybe I can give a hint. V1 equal to capital Q into A1 V1. Or if you don't want, like maybe I can simplify in this way. Q equal to sorry Q by A. Sorry, V1 equal to Q by A. Maybe I can written as Y1. This is one hint. So when you know the V1, you can calculate the F1 as V1 upon square root of G into Y1. So G can be considered as 9.8 meter per second square. This is acceleration due to gravity. Can you like quickly substitute this value into the equation and guess the answer? Anybody? Nikesh or Mukesh or Likita, how much is the answer?
Actually, I'm traveling. I don't have pen and paper to calculate.
Okay, fine. Sure. Yes, Mukesh, you raised your hand. You have any question?
Yes, and I had regarding that reoccurrence period.
Okay, so maybe that we can discuss after this question.
Yeah, sure, sir, sure.
Okay, so can you guess this answer this question?
Yes, sir, I'm doing that.
Okay, thank you. So let me share my screen again. Okay, maybe I can go to the solution. So what you will do, first step, what you will do, you can calculate the V1. How much is a V1? So V1 is nothing but Q divided by Y1. Okay. So from that equation you can get 19.56 meter per second. Okay. So substitute this particular V1 into this Raoult's number V1 divided by root over G into Y1. Okay. From that by substitution you can get a Raoult number as 9.20. Okay. So once you know the Raoult number, directly you can substitute in this particular equation. Y2 divided by Y1, 1 by 2 square root of 1 plus 8 F1 square. So here F1 no and Y1 also no. So only unknown is Y2. So by substituting this particular value, you can get a 5.759 meters. So the option C is correct. So option C was 5.77 meters. Okay. So this is a correct. This is a value. So just cross check with your answer also. And if I made any mistake, please. Huh?
Yes, sir, it is. Yes.
Thank you. So let's move to the next question. This is also from GATE 2011 only. So this question number 41. The similar type of question, if you just remember this concept, the similar type of question is there in 2011, 2014, 18, 2020 also recently. Just a straightforward question. This is a very straightforward question and very simple to score, very easy to score. I mean to say. So let me read the question for you. In an aquifer extending over 150 hectares, this is the area, the water table was 20 meter below the ground level. Suppose this is the ground level and the groundwater level is 20 meter below the ground level. Over a period of time, suppose over a period of time, suppose if over a period of time we are taking water from the groundwater, then the water table dropped to 23 meter from the ground level. Okay, this is a scenario. And they observed that the porosity of aquifer is 0.4 and the specific retention of the aquifer is 0.15. Now they asked to calculate what is the delta S. He mean to say that change in the groundwater storage of the aquifer. Okay, this is a question. And the similar type of question is like you can observe in all the previous year questions, previous year papers. So the main first relation, fundamental relation is that porosity is equal to specific yield plus specific retention. All of you know porosity is nothing but volume of voids divided by the total volume. Okay. So under the saturation, the maximum amount of water can accommodate is this particular volume of voids only. So under the saturation, all the volume of all the voids will be filled with groundwater. So that is a maximum it can store. Okay, but under this maximum storage, aquifer can only release a certain amount of water under the effect of either you do pumping or either do it by gravity. Only out of this total volume, only certain volume will be released and the remaining volume will be retained in the aquifer. So I'll give one analogy here. Let's say you take a sponge. Okay, now imagine this sponge as aquifer. Now you dip this sponge into the water. Okay, now what it will happen, the sponge sucks the water. Okay, now you take the sponge out. Okay, now you take the sponge out, let it dry. Okay, let it dry for a while. So after a certain time you just squeeze it. Now you measure what is the amount of water is like drained away from the sponge when you squeezed. So that amount you note it down, and remaining, and after you squeeze also, still if you observe, the sponge will be wet only. Okay, so now, like how you can do this experiment is can be done very simply. Like let's say you can calculate the weight of the sponge before, weight of the sponge, weight sponge, and after squeezing, what is the weight, and after with weights you and density you can calculate. So what I meant, essentially meant, is that after squeezing, still some water will be left in the sponge. That is nothing but a specific retention. That amount of water is nothing but a specific retention. When you squeeze, what is the amount of water will left to the sponge or drained away from the sponge, that is a specific yield. So that is the analogy I want to give. So given, so what are the given data? One is porosity 0.44 they have given, and specific retention 0.15. It's nothing but amount of water retained in the aquifer even after the drainage or after the influence of gravity and other things. And what is the amount of area? 150 hectares. So now from the situation we can see the change in the groundwater depth is how much? 20 minus 23 minus 20, it is 3 meters. Now our interest is to calculate the delta S. Okay, this is a very straightforward. Now you know the this n eta equal to sy plus sr. So now you need sy, so eta minus sr. So you will get a 0.25. So 0.25. So you observe the options whether they ask in hectare meter or meter cube. So in this question they ask for the hectare meter. So delta S equal to area into depth into sy, which is equal to 150 hectare into 3 meter into 0.5, which gives the value of 112.5 hectare meter. Okay, this is a very straightforward question. Okay, I hope it is clear. So that is all from my side for this today's session. So now if you have any questions, I can happily answer. Yeah, Mukesh, you have some question you can ask.
Yes, sir. I had one question related to that reoccurrence and the probability that you have showed one table to us, like
Okay, this slide.
that table of risk and that time duration that
Ah,
like
this one.
that
Ah, okay.
tables.
Yeah.
Yeah, this tables.
Hmm.
So you were explaining something out of it, like as T and N, like they comes together, their value coincide, the risk increases. So could you please explain that again? I was not able to catch that point. So.
Okay. Okay. Let me go back to this slides from home. Suppose. Okay, now imagine n equal to 100 years. This is our design life. Let's say we either design or cultivate. We imagine that it will serve the purpose for 100 years. Okay, this is our interest. Now we know this equation: T equal to 1 by 1 minus 1 by r whole power 1 by n. This is a relation we get by interchanging these terms. Now let's imagine. So, what is our as a water resource engineer aim is that when we design any structure at hand, we must know what is the risk we are willing to take. So why I am saying this is that, so let's say if I design my structure for this 950-year return period, the cost will be almost 3 times than the return period of 150 145 or 100 years. Okay, so now one has to make a trade-off between the cost as well as the return period. Okay, that is a design concern. Okay, now let's say imagine I have a risk. Maybe I want to, the risk I'm willing to take. Let's say if I make 0.10 and I'll calculate the return period. Suppose when the risk is low, the expected recurrence interval, it means that the time elapsed between occurrence of two events. What I mean is that, let's say suppose let's say 90, like one stream flow value observed at some time in the past, and after some 950 years you may able to observe this particular event, another event. Okay, so this 950 years represent here the expected time that stream flow at least once it will exceed the design value. Okay, so for this value we know that the risk is zero point 0.1. So at hand we know that we are willing to take risk of zero point 0.1, and let's say if I take the risk of 0.15, then I'll have a return period, expected return period is 616. Suppose if I want to take a risk of zero point 0.2, I'll have a lesser return period. As we go, suppose if I want to take more risk, then the return period of design return period will be reduced, and correspondingly the cost will be reduced. So what as a practitioner we do is that we at hand we know that how much risk we are willing to take. Either I want to take a zero point 0.3 risk or 0.35 risk. So correspondingly I'll choose the design life as well as the design return period. So that is a way. But related to your question, that suppose if I yeah, this I partially answered the question, but more precisely, let's say if I put a like increasing values of risk, the return period value is decreasing. So that is what I meant here. Okay,
Yes, sir. Thank you, sir.
did I confuse you? Right? Did I made it clear? Sorry if I confused you a lot. Okay, so that is all from my side for today. So it's 6:52. Maybe if I can stay for a while if you have any questions. So in the next session also I typically do the same. I'll introduce one topic. I'll introduce, maybe we'll go to this losses in pipes, either frictional loss or this kind of topics, because that is like a most interesting and important topic. And definitely you will get a 2 marks question from that, like pipes in parallel, pipes in sequence.
Yes, sir. Like today you gave us the analysis of that question, that n is equals to sy plus sr, that relation. Yes, sir. Even I was looking into the previous year's questions bank. The similar question was asked two, three times, like
Correct,
after the span of 2, 3 years. That is like questions are very repetitive in their nature, sir.
so that my session I'll pick up those type of questions only to give the best advantage for of these sessions. Okay, so please do attend for the next session also. So next, in the next session I'll talk about this losses in pipes, like major losses, minor losses. For initial first 30 minutes I'll introduce the topic, like what are the major losses in the pipes, like a loss due to enlargement, loss due to exit, loss due to entrance. All these formulas we'll introduce, and we will after that we'll see the two cases of pipes in parallel, pipes in sequence, like how we can get the losses. So and at the end I'll solve one problem, most important problem, when two reservoirs are connected with the either parallel pipes or sequence pipe, how we can collect the head and one reservoir. This is a very common problem you can see in all the gate papers. Two reservoirs will be connected with either two pipes or two pipes either in a sequence or parallel. These type of questions we'll solve in the next session. Thanks for joining today. I hope this session is useful to you. Thank
Yes,
you.
sir. Thanks a lot, sir.
Hmm. Thank you. Bye.